Hi guys, welcome to today's lecture on finite state machines using Vhdl as a part of our Vhdl lecture series. So today's lecture is a advanced concept which requires the knowledge of the if-else statements, the case select statements, and the clocked process. So I am assuming that all of y'all watching this lecture have already gone through the lectures on the if-else and the case statements and the clocked process. So as a part of today's lecture, I will discuss what is a FSM or finite state machine. I will discuss the basic components of a finite state machine, which is a next state logic, output function logic, and state memory. Then we will understand a basic FSM example. We will look at how to program FSM in Vhdl, and then we will look at a practical example of a divider circuit and a divider circuit in Vhdl. Action. So what is a finite state machine? As the name suggests, it's a kind of a machine, a circuit or a system that goes through a finite or a fixed number of states. It has a fixed number of input-output combinations. Keeping the definition aside, what is it used for? You can use it to control applications, to monitor applications, to calculate values, for communication purposes, for controlling simple and complex machines, and also to implement simple user interfaces. So let me be clear about one thing, that an FSM is a way of designing circuits. It's a method. If you find a circuit that is designed as a finite state machine or an FSM, you can design it using other methods as well. So if somebody tells you that I have designed an FSM, then if you wish to design it in another method or another way, you can choose to do so. So in short, FSM is just a way of looking at a design, because if you can define a circuit that goes through a fixed number of states, then you can call it a FSM. I hope the basic definition is clear, but as we look at more examples, things will get clearer. So to describe a FSM, you use something called as a FSM state diagram. An FSM state diagram, as the name suggests, has states and state transitions. So let's look at an example. Suppose if I have a simple FSM of 3 states: state A, state B, state C. So these would be my states. The name that I gave here, SA or state A, is optional. You choose the name. Okay? Now In every state, you define what you will do and under what conditions, if any. So if there are any conditions here, you can choose if under those conditions what you are going to do. For example, if m is greater than n, this is just a dummy example that I'm taking. Please understand the concept. I will take a practical example of a divider in the next few slides. So if m is greater than n, then x must get a and y must get b. So under the condition that m is greater than n, x will get a and y will get b. Then if I would like to go from state A to state B, then I would write x greater than y. Again, this is just a dummy example. Please don't try and understand the logic of this state diagram, just understand the concept. So this transition is called a state transition. So if x greater than y, I would go from state A to state B. In state B, I simply do y gets A and x gets B. So here there are no conditions. If I would like to go from state B to state A or state C, then let me take the condition if A plus B is equal to 1. So if A plus B is true, I can also write this as just A plus B, which means that if A plus B is true, then I will go from state B to state C. And then from state C to state A, I will go when B is true or B is 1. Okay, this is just a simple example. So here we understood how do we draw a FSM state diagram with a different states, state A, state B and state C. And then we also looked at the state transition diagrams here and here. Now this is a basic state machine state diagram which helps you, define and describe a FSM. So if I choose, I can remove these conditions also. Again, this depends on your application. So these conditions that I just removed would depend on your application. And we will see that as a divider, as an application, we would see that. So now this is a basic state machine. I would like to explain a few rules to the user. So let's understand that. The first rule of FSM states that the state transitions, that are these transitions, must be mutually exclusive. Now what do I mean by mutually exclusive? Let me take an example which is right here. So if my x is greater than y, my state machine must go from state A to state B, which is fine. But what if x is less than y or x is equal to y? Then what? Then my state machine is confused because I have not mentioned this here at all. So I have to specify conditions that if x greater than y bar, which is opposite of x greater than y, then my state machine must come back to state A, which means that the conditions that are coming out of a state, so the conditions that are coming out of a state must be mutually exclusive, or in simple terms they must be opposite, so that my state machine is not confused. It always knows where to go. Please, this is very important, that your state machine must always know where to go. It cannot be confused and stay there. Okay, this is very important in terms of state machine design. Similarly, can you think what must be the mutually exclusive component of this? I simply need to write A plus B bar, and this would be B bar. So the first rule is mutually exclusive. The second rule states that all these conditions, the conditions, let me write this here. So the conditions coming out of, please be important, out of a state must be first mutually exclusive and all inclusive. All inclusive means that this condition and this condition must cover all cases. So they must be opposite, or mutually exclusive, so that the state machine is not confused, and it must cover all cases so that no case is left out. Okay? Just to revise again, that the state transition diagrams, you must try and keep them mutually exclusive, and they must cover all cases, that is all inclusive. These are fundamental rules. These are fundamental rules of FSM design. Please understand that. So now that said, if I have a state diagram like this, how do I program that in Vhdl? But before that, you need to understand the components of a FSM. So given a state machine like this that we just saw, let's understand what are the basic components of a state diagram. First, I have something called as my NSL, or my next state logic. I have something called as my OFL, or my output function logic, and in between I have something called as SM, or state memory. Now let's understand what each of these do. My NSL helps me, which is the FSM, decide which state to go under what conditions. So the fact that I go from this state to here on x greater than y is decided by my NSL. My OFL it helps my FSM decide what to do in what state under what conditions. So If I am in state A, I need to do this operation. Currently there are no conditions, so if I'm in state A, I will give A to X and I will give B to Y. Okay, I will give B to Y and A to X. So that is helped by the OFL. The state memory helps me, that is the FSM, remember what state I am in. So this is my state memory. Because how will my NSL know what state I am in? My state memory helps my NSL and OFL understand, look, I am currently in state A, I am currently in state B, and then my NSL will decide, okay, I am in state A. Now I will check if X is greater than Y, then I will go to state B. So now my state memory will change to state B. In state B, my NSL will see if A plus B is 1, yes, then I will go to state C. So then my state memory changes to state C. I hope this basic concept is clear, that the three major components are the next state logic, the state memory, and the output function logic. So now, given this kind of a structure, that these are the components and this is an FSM, how do we write this in VHDL? First, you would model your NSL, that is your next state logic, using if-else statements. It makes sense that since you have if you look at these conditions very carefully, if X greater than Y, then my state should be SB, else my state should be SA, which is if X greater than Y, I come here, else I stay here. So this can be modeled using a if-else statement. Now each state can be modeled using a case statement. If you remember, I can say case state is when SA, which is when I am in state A, I will say X is A, Y is B. So this is your case statement. Now a little more technical point, which is every state variable, or that is SA, SB and SC, I will define as a constant. We will see this in the example. And your OFL, which is your output function logic that I've just written here, will be conditional assignments. Since there was no condition here, there was no condition here. But if there was a condition, then you will have a condition statement here. So let me repeat this again. That first, my NSL, since there is conditional logic here, I will define it using the if-else statements. Each state that I have is modeled using a case statement. For example, case state is when SA or when SB or when SC, if you remember the case statement. Now the output function logic, or what happens inside each state, is defined using conditional statements. If there are any conditions, if there are no conditions, you will have direct assignments. Okay, well, let's look at this example, this particular example in VHDL. So assuming that you have written the entity, let's look at what the architecture of this FSM would look like. First, I would define my signals X and Y, and then I would define my states as three constants of the type standard logic. Now, since there are three states, my total number of possible combinations are 3, and this style is called one hot coding. I will explain this. What we mean by one hot coding means that each state represents one unique data bit which has only one single bit as 1. So if you see, SA is 001, SB is 010, SC is 100. So this style is called one hot coding. This is a good design style, so hence I am teaching you this. There are other design styles for FSM as well, but it is a safe option to stick to this. So each constant defines one state of the type standard logic vector. Vector means that if you have more than one bit, then you define it as a vector. 2 down to 0 means 3 bits, and as you can say, it can take the value 001. Constant SB, which is your state B, again 010, constant SC 100. Now, that said, these constants are just numbers, but you need a signal which can take these constant values, and hence you will define a signal called as state. Please understand, this word state is not a keyword. You can define this state, you can call this state X, you can call this define as John, you can call it whatever you want to. So please understand that the word state is not a keyword. That said, it is very important to understand that the signal state must be the same size as your constants, because the value of the signal should be able to hold these constant values. Okay. That said, let's look at the actual FSM part. Now, obviously, I would go from one state to the other on the edge of the clock. So this must be a clocked process. So if rising edge clock, which is a clock process, then inside that I write case state is. So this will be a case select statement. Case state is when state A, that is when state A, I write my OFL, that is output function logic, that X must get A and Y must get B. Then I write my NSL. Please understand, I define the state, then I write OFL, then I write NSL. You can choose to write NSL first, then OFL. That is okay, no problem. Here we just took OFL first. So first I write my OFL, which is X gets A, Y gets B. Then I define my NSL, which is if X is less than equal to Y, which is the opposite of X greater than Y, I come to state A, else I stay in state B. Basically, we wrote this opposite. I can also write this as this same statement as if X is greater than Y, then state is SB, else state is SA. both are one and the same. Okay, so what I would like you to understand here is the NSL, or the next state logic, is written as a if else statement. Okay, now similarly I will define for SB. So let's look at that. Now state B is also part of the case statement, where we are writing the case statements like when SA, when SB, and inside that I'm writing the NSL and the OFL. If you remember, inside a case statement I can have if else statements, and the vice versa is also true. So that said, let's look at this. So when SB, I write my OFL first, that is y gets A, x gets B, and then I write my NSL, which is if A plus B is true, then I will go to state C, else I will stay in state B. Okay, that is quite straightforward. And when I have state C, I say if B is 1, which was this condition, then I go to state A, else I stay in state C, which is here. So again, this was your NSL, or your next state logic. Now, just for correction, there should be another case here, which is when others. If you do not have a when others, that is wrong. You must have a when others. So the safest option is to put the initial state is SA. This is good and safe design. Okay, so just to summarize that, when I'm doing FSM using Vhdl, I first define my states as constants. The width of the constant, or the number of bits in the constant, is equal to the number of states, which is for one hot coding. Then the size of the signal which will hold these constants will be equal to the size of the constant. Okay, makes sense? Then I will define each state as a case, and inside those states I will define my OFL and my NSL here. Okay, so now let's look at a more practical example, which is your divider. Now if I want to divide two numbers x and y such that x divide by y, how would I do that? I would first take x and then do x minus y. Let's take 8 and 3. If I'm doing 8 divided by 3, I would first do 8 minus 3 is equal to 5. Quotient is 1. Then 5 minus 3 is equal to 2. Quotient is 2. Now I can't do 2 minus 3, as that would be a negative number. Hence my quotient is 2, remainder is 2. This is a very simple method of doing division. So let's look at how to do division using FSM. Suppose if I have a state machine such that my initial state, I have my x variable which gets the input value A, I have my y variable that gets input value B. So I'm doing A divided by B, which would be x divided by y. Okay, then I press the start button and then I compute or calculate if x is greater than y, greater than equal to y rather, because even if they are equal, it's fine, x would get x minus y. My quotient would be quotient plus 1. If you remember, 8 divided by 3, I do 8 minus 3, which is equal to 5, and put it back into x, which is 5. Then I do 5 minus 3, and then I put it back here. Okay? Now, the condition would be that if my x is less than y, so if it's the opposite of greater than equal to y, so as long as my x is greater than equal to y, I keep doing this calculation. If my x is less than y, which is basically the opposite of this, so I can write this or this, then I will say that I am done, such that my remainder r gets the current value of x. Okay? And from done, I can go to the initial state without any conditions. So when I write 1 here, that means no conditions. Okay? 1 equal to no conditions. So very simple divider example. I've made a small mistake here. Can somebody point that out? Can you think about that? Remember when I said that it should be mutually exclusive, all inclusive, then this should be start bar. Okay? Now on that same note, do I need a condition here? No, because no matter what, under no conditions I'm going here. Hence this is mutually exclusive and all inclusive, because the value 1 is all inclusive. Okay? I hope that is clear. So now let's think of how to implement this in VHDL. I hope this divider example is clear, that as long as my x is greater than or equal to y, I keep doing the subtraction, that is x is x minus y, and I keep incrementing the counter, that is q plus 1. So let's go through the VHDL example of this divider. So just for the user's convenience, I have put this in 2 separate windows next to each other, and I would like to explain how this VHDL code works. So as you know, that first I would define my constants. So I would have my constants initial, compute, and done, same as here, here, and here. Then I would have my signal state, which would be the same size as my compute, initial, and done, just as before. Now let's understand the FSM. Obviously you would have the begin statement for the architecture here. This is for the architecture. Now it's a clocked process, so process clock. Then I say if rising edge clock, which is because this FSM will be from on the edge of the clock, I would go from state to state. First I would do my OFL, so x gets A, y gets B, same as here. Then I would start my NSL, which is if start is equal to 1, then my state is compute, else my state is initial. That is, if my start is 1, then I would go from here to here, else I would stay here. Similarly, for my compute state, I would write the OFL first, which is if x is greater than equal to y, then x is x minus y and q is q plus 1. Then I write my NSL, which is if x is greater than equal to y, then I stay in my compute state. So if my x is greater than equal to y, then I stay in my compute state. Else, which is the opposite of this state. So whenever I write else, you can assume that it will always be the opposite of this state. Then I say my state is done. Okay. Now when I'm done, I don't have any OFL because I don't have an NSL, I just have an OFL. So I write the OFL statement here. This is my OFL statement, which is R is X, means the remainder gets X, and the state that I have to go is initial. So here there was only OFL, no NSL. Okay. Similarly, when I write this here, there is no condition. Like for example, here in the NSL there was a condition. Here there is no condition, so I just write state is initial. Okay. And again, as I said, when others, I have to write a safe condition, so my state is initial. Okay, then I have an end case. This end if is for my this if rising edge clock, and this end process is for the entire process. Okay, I hope that this divider example was clear. We look at this divider example as part of the example. Okay, now one very important point, how does my FSM know that this is happening at the edge of the clock? How does my FSM know that this is happening at the edge of the clock? The answer is here. This. Remember when I said that any assignment statement under the clocked process will give you what? Will give you a flip-flop. So any assignment signal under a clocked process gives you a flip-flop. So each state assignment that you say state is SA, state is SB, will all be a flip-flop. So now your state, which is a standard logic vector 2 down to 0, which is 3 bits, will actually form how many flip-flops? 3 flip-flops. Okay, the 0th bit, the first bit, and the second bit. Similarly, your X getting A and Y getting B, so your X and A will also be, your X and Y will also be what? Flip-flops. Similarly, your Q and your R both are assignment statements under the clock. Hence, Q and R will also have a flip-flop. This is very important from the concept of design. Hence, you need to remember this point. So I hope this lecture on FSM design was clear. It's a advanced topic. Hence, I encourage you to understand this carefully. So we understood the concept of mutually exclusive all-inclusive. We looked at a state machine diagram. Then we understood the basic rules of FSM, that is mutually exclusive all-inclusive. We saw that an FSM has a next state logic, a state memory, and an output function logic. My next state logic helps me decide which state to go to under what conditions. My output function logic helps me decide what to do in each state, and my state memory helps me remember which state I am in. Then the writing of FSM in VHDL, we wrote the states as constants, and then we assigned a signal state which will hold these constants, and then we wrote each state as a separate case, and under that case we wrote the OFL and the NSL as conditional statements. And then we saw the example of a divider, a practical example, and we saw how to write that divider in VHDL, the same concept where each state is given a constant, then we have a signal to hold that state, then the clocked process, the case statement to write the state, then the different cases, and then we write the OFL, the NSL. If you see, this is a conditional OFL, this is a conditional NSL, and then we close the program with the end case, end if, and the end process. So as a part of the lab, you will see how to implement this. So I'll see you in the next lecture. Thank you.